All right, thank you, Tyler. Welcome to everyone. Today's presentation is going to be similar to most of the others. We have a lot of material to cover, and I usually do this presentation in an hour and a half or 2 hours. And so I wish I could do it to each one of you in person. It'd be a lot more fun, but those were pre-COVID days. So hopefully they'll come back one of these days. In any case, we're going to be covering this material in about 45 minutes. So I'll be moving pretty quickly through it. We're talking about how to size a standby generator. Here's some of the items that we're going to be covering. Here's 10 points of sizing pain. And you can see that sizing a generator involves a lot of items. And so thank goodness for computers. Generator programs generally size a few discrete loads and they do okay. The generator, the ones on your computer, of course, generally came out to try to analyze the starting of a motor. And they did a pretty good job of that. Perhaps you've noticed that in the last few decades, our world has gotten slightly more complicated. And we have VFDs, we have soft starts, we now worry about harmonics, something we never did before. And so generator sizing programs have not necessarily kept up with that, but we will show you a generator sizing program a little later that has won a number of awards. Really is very easy to use and is a great program, and I highly recommend letting the computer do the work. There are generally 3 ways to size a generator, and this indicates some of the limitations of typical generator sizing programs. The first way to size a generator is with the utility bill. And with the utility bill, we generally want to, a lot of people will come to me and say, hey, here's my utility bill. We use so many kilowatt hours. Can you size a generator? No, that's completely useless information. But if you say, here is my demand in kilowatts, now that helps. And I want to know a little bit about the load, a little bit about the harmonics, a little bit about what the largest motor might be, but otherwise I can pretty much use that demand as long as I have a whole year's worth. Because if I have a demand for April and we weren't using the air conditioning, that demand may be completely different in August. So we can look at that, and generally we never load a generator to more than 80% when we're doing that. That's called engineering conservativeness or engineering slop. However, it's also really just a smart thing to do. Number one, you never really want to load generators right to their maximum, because if you end up going over that maximum, you can cause the generator to trip. Also, you can get wet stacking in diesel generators. That will affect their highest load. But finally, that kilowatt demand is your highest 15-minute average. And if you're looking at the highest 15-minute average, you know that your actual peaks have gone above that. So that's the first way, the utility bill. The second one, actually measuring it. Tell someone to turn on all the loads and then measure. And then I like to use the 80% rule. And the third way is with engineering drawings. That's the way we tend to do it probably the majority of the time. You'll find that when you size generators per engineering drawing, go out during a power outage, you will find generators are about 50% loaded. So you might say, well, that means we do a terrible job of sizing generators. Well, actually not. I think we do a great job of sizing generators, and nobody complains about an oversized generator. And the fact that it's 50% on average doesn't mean it's not going to go higher than that at certain times of the year. But that tends to be about the average loading on a standby generator, about 50%. Now, when we do analyze these things, we need to look at resistive loads, motor loads, and nonlinear loads, and we're going to talk about all of those things. We're going to also talk about paralleling, and paralleling generators is a very smart thing to do. Paralleling generators allows you to anticipate load growth and not have to buy more than you need. It also gives you redundancy, makes servicing easier, and is really a very, very nice thing to do for emergency systems where it's really critical that that generator be online. But we're going to do a whole webinar on parallel generators, and so we're not going to do that today. What are the largest load steps on the generator? Very important point, because I've seen many, many generators that were plenty big enough to run the load, just not big enough to start the load. Starting the load, we're talking about motors now, generally much more difficult than running the load, and we will talk about that coming up. Before we do that, what voltage drop is okay? If I say to you, what voltage drop are you comfortable with? Well, I get answers when I'm doing this thing live all the way from 5% to 30%, and those are all okay. Those are all decent answers. But I will say that if you go 30%, you are likely to have significant problems, because you're going to have contactors dropping out, solid state devices dropping out, elevators won't work. You're going to have a lot of problems at a 30% voltage drop. On the other hand, a 5% voltage drop is going to make it extremely difficult, because you're going to end up with a hugely oversized generator. And while I'd like the 5%, it's just typically not practical. So I would tell you that my opinion is I like to stay under 15%. A lot of solid state devices, elevator controllers, for example, they're going to drop out at 15%. So I really get the warm and fuzzies when I keep my voltage drop to 15%. Now remember that we're only talking about a voltage drop that's probably going to last less than a second, only a portion of a second, but that's a long time for little electrons who are really fast. On a steady state basis, generators are going to be right at their programmed value. We'll say 480 volts on a 480 volt generator. But when you start a large motor, or when you start any load, you are going to get some voltage drop until that voltage regulator has time to respond. And I really like the 15% figure. Now, if you know that you don't have solid state loads, I feel somewhat comfortable going up to 20%, but I worry a little bit in that 5% range. And anything more than 25%, I really wouldn't do unless I carefully analyze the system. We've had jobs where engineers did this, carefully analyzed the system, put a DC contactor on their motor, said, no, we just starting one motor and it can hang in down to 35%. And then some little control relay, a little ice cube relay somewhere drops out and messes the whole thing up. So there's my opinion on voltage drop. Now, frequency drop's less important, and we generally try to get that between 5 and 10%. But the only loads that tend to be real sensitive to frequency drops are uninterruptible power supplies. Okay, we talked about this earlier, your billing history or using a meter to measure. Power factor. First of all generators are rated at 0.8 power factor. Well, actually, I just lied to you. All three-phase generators are rated at 0.8 power factor. Single-phase generators are rated at 1.0 power factor. We do that just to confuse you. So think about this for a minute. If a generator is rated at 0.8 power factor, that means it's going to have a full load current on the generator. You can only reach that full load current if you are at 0.8 power factor or less. If you try to reach that full load current and your power factor is higher, you are going to reach your engine kilowatt limitation and you're going to trip that generator. So remember, you can't necessarily get full load amps on a generator. It depends on your power factor. Now, you can get full load amps on a single phase generator, but not on three-phase. So on three-phase generators, if the power factor is less than 0.8, you are going to be able to hit full load amps, but not full load kilowatts. If it's higher than 0.8, you're going to hit full load kilowatts, but not full load amps. And I'd like to spend more time on that, but we simply don't have time in this quick format. Leading power factor, generators don't like leading power factor. Suffice it to say that when you're trying to push VARs into a generator, it's going to have to reduce its excitation in the generator, the magnet that basically rotates and creates your output voltage. And the more leading VARs you have, the more you're going to reduce that, and eventually you're going to get to the point where you don't have enough magnetization, enough excitation in that rotor to keep the generator stable, and the generator is going to go unstable. So in general, we want to keep capacitors off of standby generators if possible. You can do this pretty simply by putting your capacitors on the normal side or the utility side of the UPS or the automatic transfer switch. And then when it switches to the generator, the capacitors are automatically disconnected because they're over on the utility. Another problem that's fairly common is harmonic filters on drives. They have leading power factor when they're at lower loads. We can solve that generally pretty quickly by simply putting in an isolation contactor, or what we call a cutout contactor on that, and that will pretty much take care of the problem. Generators can take some leading power factor, but it must be within the reactive capability curve of the alternator, and we don't have time to really get into the details of that. But a little leading power factor, not necessarily bad. Lots of leading power factor can cause generator instability. Okay, here's some of our key point summaries. Now let's talk about motor starting. Typically, a generator is composed of an engine and an alternator. Well, those do not need to be the same size. Now, it turns out by UL, the alternator must be at least as large as the engine. However, the engine does not need to be as large as the alternator. So it's very, very common for us to oversize alternators, and we're going to be talking about why we do that in a moment. This is a motor starting curve for a motor, and you'll notice when you start a motor, you get about 600% current. You get about 600% current there at 0 speed, and then as the motor comes up to speed, that current drops down. And as we talked about in previous seminars, once you get to about 150% of full load, then you're in what we call the linear portion of the motor operating curve. And from 150% to about 50% load, the current is proportional to the torque. But we, with our standby generator, don't just need to run that motor, we need to start the motor. And so when we start the motor at 600% current, the generator needs to supply that. And when it hits all of a sudden, we can get some pretty severe voltage drops. Let's do a little calculation here. SKVA. SKVA is going to stand for starting kVA. So it is kVA, of course, thousands of volt amps. And S means starting. This is when we start our motor. So that's equal to the line-to-line voltage times the locked-rotor current times square root of 3 over 1,000. Of course, that's true for three-phase loads, not for single-phase loads. So let's take a typical 100-horsepower motor, and that 100-horsepower motor is going to have about 750 locked rotor amps, maybe 115 full load amps. And so our starting kVA will be 480 times 750 times the root 3 divided by 1,000. And then knowing that starting kVA, we can go to the alternator curves and find out what our voltage drop is going to be, or let the computer do it for us. Now, there is an easier way, because this is a little difficult to do in your head, right? Multiplying things by square root of 3 and 750, that's difficult. So this is an easier way to do it. And we simply look at the starting codes. Starting code gives you kVA per horsepower. So most starting codes on most motors are F or G. So we'll be conservative and go G, and then we'll find a nice round number there, and that nice round number between 5.6 and 6.3 is 6.0. So if I have a 100 horsepower motor, I just multiply by 6 and I get 600 starting kVA. And you can see that's pretty close to the 623 that we calculated over here. We do not size generators to 3 decimal places. We always have some conservativeness in there, some engineering slop. And so this is a great way to figure out what your starting kVA is. And on that we do have Generac. You can get actually CEU credits for all 50 states by doing this. If you want to take their test, this would be a good thing to know. This slide basically just says some special motors are not F or G and can have different starting codes, like a downhole submersible pump would certainly be different. But for most motors, 6 kVA per horsepower looks pretty good. Now here's what happens. You close the motor across the line. We're talking about a full voltage non-reversing starter. and boom, the voltage goes down. Then the voltage regulator sees that the voltage has gone down and quickly causes that generator to recover. It does this in much less than a second. So it happens very quickly, but if it drops too low, you could have contactors falling out, you could have PLCs falling out, elevator starters falling out. So that sudden drop is very important. And if you're measuring this with your Fluke multimeter, you won't even see it because it'll drop and it'll recover before that meter even updates. So look at curve A over here. Curve A, we have a 10% voltage drop, and then it gets bigger and bigger. Curve B is 50% voltage drop, and curve C is 50%. Did I say that right? B is 35%, C is 50%. As I said, how much is sufficient? Well, I really like to keep things less than 15%. I start getting nervous when it goes over 15%. But if you talk to a generator salesman, he will learn probably in his first week selling generators that that generator has no problem with a 35% voltage drop, excuse me. And it will recover to 100%. Remember, it's going to drop to 35, but in less than a second, much less than a second, it's going to recover right back to its full 480 volts. But in that time, a lot of things could go wrong. So a rule of thumb for generators is they need to be twice as large as the motor. For instance, if you have a 100 horsepower motor, the generator should be 200 kilowatts. Well, that's a true fact, but you're going to have a 30 to 35% voltage drop. And so even though the generator is able to start the motor controller may fall out. So this voltage drop is very important, not just to use a rule of thumb like 2 kilowatts per horsepower, but rather actually analyze that, see what your voltage drop is going to be, and make sure you're comfortable with that. Now, if you go too far, then it cannot recover to full voltage. If you try to suck too much out of that generator, you are not going to be able to get back to full voltage. We call this the 90% sustained recovery voltage. Cummins tends to publish that number. Other people tend not to because they say that if you're at that point, you really misapplied the generator. If that generator cannot get back to full 480 volts, then you've misapplied the generator. Now, you can see the 90% sustained recovery is on the verge of voltage collapse, which brings me to ask, what is the short circuit current on a generator? The answer is, it is 0. Generators do not have any capability to produce short circuit current. Why is that? Because the way you produce a voltage on a generator or current is you take the 480 volts off the line, you put it through a rectifier, then you put that DC current into the field of the generator through the voltage regulator, and that magnetizes the field, and then you have a rotating magnet which can create your output voltages and currents. If you have a short circuit, then that 480 volts collapses. When it collapses, there's no power available for the voltage regulator, and therefore no current into the field. Therefore, that field simply collapses. Your magnet inside the generator collapses, and the generator becomes a big rotating piece of dumb iron. It doesn't work very well. So we want to stay away from that 90% sustained recovery voltage, and we want to remember that in a true short circuit, you're not going to have enough current to even trip the breakers downstream. The generator will collapse. Now that I told you that, I will tell you that I just lied to you, because you can get generators that are permanent magnet brushless. And in those cases, they put permanent magnets into them so that they will generate 300 to 350% short circuit current to allow you to generate that much current while there's a short circuit. Hopefully there's a breaker downstream that will then trip and the generator will recover. But all generators do not have permanent magnet alternators. And so if you have an emergency or legally required generator, it is required that you use a permanent magnet alternator. With Generac, anything over about 150 kilowatts, we provide that permanent magnet alternator free of charge. Well, I shouldn't say free of charge. We just don't charge extra for it. But on smaller generators, they tend to be brushless or simply direct excitation, which we will talk about in our alternator class. And they don't have that permanent magnet. They are going to collapse during a short circuit. All right, enough said about that. Why does a generator voltage dip? Because they have very high subtransient reactance. And when you get high currents, you're going to get large voltage drops in the subtransient reactance of the alternator, and it's going to cause a large voltage drop. Now, again, the voltage regulator will still bring it right back to 480 volts, but that may be too late. Your load may have already tripped. I would like to spend a lot of time on this, but due to time, we're just going to look at it very quickly. We have a 100 horsepower motor that's going to have about 600 starting kVA. We look at our curves and find out that, first of all, we need a 200 kilowatt generator, because that's the rule of thumb, right? 2 kilowatts per horsepower. But you'll notice that that standard 200 kilowatt generator comes with a 200 kilowatt alternator. And that 200 kilowatt alternator is going to have about a 35% voltage dip. So yes, the generator is okay. Yes, the generator can start the motor, but can your system tolerate a 35% voltage drop? The answer is probably not. So what can we do? Well, the engine is okay. It's big enough. It's the alternator where we have a problem. And the alternator may be only 15% of the cost of the generator. So we can oversize that alternator. Very low cost. The generator isn't going to get bigger. The fuel tank isn't going to get bigger. The fuel filters and everything are going to stay the same size. We simply put in a bigger alternator and we get less voltage drop. So that's the first reason to consider putting in an oversized alternator. And we sell a lot of generators with oversized alternators for this very reason. Now, if we go to 230 kilowatt alternator on a 200 kilowatt generator, we can reduce our voltage drop to 25%, excuse me. If we go to 275 kilowatt alternator, then we can reduce our voltage drop to 20%. If we wanted to reduce our voltage drop to 10%, we would need to go to a 750 kilowatt alternator, which actually is not going to be available because it simply won't fit on the frame of the 200 kilowatt generator. So moral of the story is, at large voltage drops, you can get voltage drop improvement quickly and cheaply by oversizing the alternator. If you want to get up to very, very low voltage drops, then it gets a little bit ridiculous and you have to consider some other things like a solid state starter. So if somebody says, I want a 5% voltage drop, you can see that that just isn't going to happen if you're starting one motor. Now, typically generators are used to start lots of loads, and of course that helps you tremendously. Now, that was the alternator. That's the voltage. The voltage is what we care about electrically, but there is another factor here, and that is the engine. The engine's going to slow down, just like when you come to a hill in your car. And as it slows down, the governor now is going to realize that you are slowing down, and that's going to cause a frequency dip. It's going to put more fuel into the generator and bring it back to 60 hertz. But it's going to take a little bit of time, and while the voltage regulator is generally going to recover in a fraction of a second, the engine speed will maybe take several seconds to get back to full speed in a worst case, very large motor start. So fortunately, as I said, most loads don't really care too much about frequency drop. All right, power factor is equal to kilowatts divided by kVA. Therefore, if you have a 100 horsepower motor, you multiply times 6, you get 600 starting kVA. Now you multiply that by the starting power factor of a motor, and you end up with 180 starting kilowatts. Now the starting power factor of the motor depends upon the motor, but 0.3 is a pretty good number. So notice here that a 100 horsepower motor takes 180 kilowatts to start. That's pretty close to the rule of thumb that I told you earlier of 2 kilowatts per horsepower. So there in the top paragraph there, it talks about the 2 kilowatts per horsepower, and most loads are very tolerant of frequency dips. So we don't tend to worry about that. We worry more about the voltage drop. All right, here's some rules of thumb. My opinion, every engineer should know these rules of thumb. They are not generator rules, they are motor rules. And any person who deals with engineering power systems needs to know this. So let's take a look at the alternator first. Your starting kVA is equal to 6 times your horsepower, and we've already talked about that. What we have not talked about is the running kVA. After that motor has started and it's up to speed and running, your running kVA is approximately equal to the horsepower. Now the engine is different. It is responsible for kilowatts. So kVA is your volts and amps. That's strictly an alternator function. But the actual power coming out has to do with the engine. It gets that from your fuel. And I've seen people say, oh, we'll take a 100 horsepower motor or a 100 kilowatt generator and we'll oversize the alternator to 150 kilowatt. Now we have a 150 kilowatt generator. No, you don't. No, you don't. The engine is still 100 kilowatt, and you do not get more engine by oversizing the alternator. So your starting kilowatts is approximately equal to the horsepower times 2, and your running kilowatts is equal to the horsepower times 0.85. Well, let's do some examples here. Now, you don't have to do these things. You can just let the computer software do it for you. But I think it's helpful to try to go through this example so that we understand how this all works. So we've got 3 motors, a 200 horsepower, a 100 horsepower, and a 50. Should we start the 200 first, the 100, then the 50? Or should we start the 50, then the 100, then the 200? Or should we start all motors simultaneously? Well, I've got a good idea. Let's do all 3. So let's start with exercise number 1. We're going to start the 200 horsepower first. 200 horsepower times 2 kilowatts per horsepower is 400 kilowatts. So we're going to need at least a 400 kilowatt generator just to start that one motor. Now, once that motor's up to speed, then it only takes 0.85 times 200 horsepower, 170 kilowatts. So I mentioned earlier in this presentation that a lot of people buy a generator plenty big enough to start their motor, or plenty big enough to run their motor, excuse me, but not large enough to start their motor. And you can see why that is by simply looking at the 400 kilowatts necessary to start the motor, but 170 kilowatts is okay to run the motor. So you can't just go to a motor and say, hey, I've got a 100 horsepower motor that's 85 kilowatts. I'll buy myself an 85 kilowatt generator. No, it'll run the motor, but it won't start the motor. Now, once the 200 horsepower is running, we're going to start the 100 horsepower. So 100 times 2 is 200 starting kilowatts, plus the 170 from the 200 horsepower that was already running. So it's going to take 370 kilowatts to start the 100 horsepower motor while the 200 horsepower motor is running. And you'll notice that that is less than 400 starting kilowatts. So 400 kilowatts is still large enough. Now, once the 100 horsepower is started, now we have 100 plus 200 or 300 total horsepower times 0.85 gives us 255 running kilowatts. Now we start the 50 horsepower, 2 kilowatts per horsepower is 100 starting kilowatts plus the 255 that was already running gives us 355. And so our 400 kilowatt generator is still big enough. Now, what's our voltage drop going to be? Well, we would take our largest motor, multiply that by 6 kVA per horsepower. That gives us 1200 starting kVA. We can go to the tables and find out what our voltage drop is going to be. But I can tell you pretty closely that since our generator is 2 kilowatts per horsepower, we're going to have about a 30 to 35% voltage drop. So I'm going to want to do something about that. I may want to put on a solid state starter. I may want to oversize the alternator, but I am going to worry about the voltage drop. Now, let's go to example number 2. In example number 2, we're going to start the 50 horsepower, then the 100 horsepower, and then the 200 horsepower. And so we're just going to save ourselves some time here because we know that 200 horsepower is going to be the hardest one. And so we're going to assume the 100 and the 150 and the 50 are already running, and they take 130 running kilowatts. Now we're going to start the 200 horsepower times 2 kilowatts per horsepower. And that is 400 kilowatts plus the 130 that was already running. We now have a 530 starting kilowatts. So we're probably going to have to purchase a 600 kilowatt generator. The generator got 50% bigger just because we started the load in a different sequence. Now, the good thing here is because we went with the larger generator, our voltage drop is going to be a little bit less. Finally, let's start all of them simultaneously. That would be a 200 plus a 100 plus a 50. That's 350 horsepower times 2 is 700 starting kilowatts. So we're going to buy a 700 or a much more common size, a 750 kilowatts. So you can see that the same loads take anywhere from 400 to 750 kilowatts, depending upon how they're started. So what is the correct answer here? Well, we sell generators. Obviously, the 750 is the correct answer. Okay, joking aside, the fact is, it depends on you. You know, if you go back here and you can start the 200 and then the 100, then the 50, go ahead and buy that 400 kilowatt generator. But remember, if the 200 ever stops, you're going to have to stop the other loads in order to restart the 200. So in a lot of cases, this simultaneous is actually the right size. But it all depends on the capability you have to control how those motors start. All right, electromechanical starters. Electromechanical starters are very helpful because they reduce the current and therefore they make it easier to start that motor on the generator. I want to point out one thing that's that's a sneaky here. And if you, let's say you start on an auto transformer starter or a Y delta, this is very common on Y delta starters. When you start, yes, you can use a smaller generator because you have a Y delta starter and it takes less starting current. But the problem is it also reduces your torque. And so let's say you have a pump, you maybe get up to 75% speed over here, and all of a sudden your motor stalls because it doesn't have enough torque to get to full speed. So then the timer times out and it goes from your star configuration to your delta configuration, and boom, you get like almost 500% current, not quite 600%, but very high. And so this area right here actually is where you need to size the generator to, because the generator has to get through that area too. And when you may find that you have a star delta starter, you're coming up, you're just fine, and then all of a sudden, boom, you switch to the delta and your generator fails. So these mechanical reduced voltage starting methods, your auto transformer, your star delta, your primary reactor, they tend to be good, but may not actually give you the benefits that you're looking for because of the fact that they cannot get that motor up to full speed before they have to switch to full voltage. Now, if you've got a compressor, let's say, you can start that compressor unloaded and get it up to speed and then load it, well, then that's a different situation. So there's our key point summary. Now let's talk about harmonics a little bit. We've had several sessions on harmonics if you've been a part of that, but harmonics are caused by all solid state loads, and they basically are high frequency currents that go back into your power system. Harmonics are very important. They can distort your voltage waveform, but in a generator, they also create much higher voltage distortion than it would on the utility. And just to give you an example here, let's suppose that you have 1,000 kVA transformer on your building and you measure the voltage distortion, it's 3%. Well, that's great because 3% is very good. The standards allow you 8%. But then you go to a standby generator and the standby generator is only 500 kilowatts rather than 1,000 kVA, which is pretty common for generators to be smaller than the transformer. Well, now with the same loads on it, your voltage distortion is going to be 6% because of the fact that the generator is only half as big. But it gets worse than that, and the reason is that the impedance of a typical transformer is around 5%, 5.75%. They do vary, but that's a typical value, whereas the impedance of a generator is probably more like 13, 14%. And so we'll assume the impedance of a generator is about 3 times higher than a transformer. And so now our voltage distortion is tripled, and that 6% times 3 becomes 18%, and that's way, way higher than the 8% that you're allowed by the standards. Now, if I'm starting a motor or something on a solid state starter, I'm comfortable going up to maybe 10% or so. But the standards say no more than 8% when you're running. So it's important, and you are going to have higher voltage distortion on a generator. And so this is important. We want to take care of that. So it is very important that you analyze voltage distortion, and my suggestion is let the computer do it for you. If you have a drive, a variable frequency drive, and it's unfiltered, in other words, you have reactors, but you don't have a harmonic filter, you're going to have about 35% total harmonic distortion, and you're going to have to upsize the alternator 2 to 2.5 times at 480 volts, 3 to 3.5 times at 208 volts, or 5 times for single phase units in order to control your harmonics. And that's the second reason to have an upsized alternator. Number one was to control voltage drop during motor start. Number two is to control your harmonic levels. Now, if you have a filtered drive, then generally we don't have an issue there. This is Generac's sizing program, which I hope that I can at least show you in a moment. And this shows you some of your harmonic distortion that you can get. So how do you calculate the harmonic distortion? Just let the program do it for you. You can do it on a spreadsheet, but I would highly suggest you let the computer do it for you. Choose easy here. Now, soft starters. Soft starters have harmonics only when they're starting, but not when they're running. This is a typical soft starter. It's got these two back-to-back SCRs, and basically they're just like gated valves, and they chop up your motor waveform. This is just like a light dimmer. And so they do generate some harmonics, but the really nice thing is on most soft starters, you get a nice smooth voltage ramp. And because of that nice smooth ramp, your voltage regulator in the generator has time to respond and slowly follow that voltage ramp up so you do not get those horrific voltage drops. How do you analyze this? Again, let the program do it for you. This is talks a little bit about your soft starter starting. The harmonics and the currents depend upon your current limit. I typically tend to use a 400% current limit when I'm doing my analysis because I found that that's often necessary. So word to the wise, when you analyze, let's say, an elevator, it's always going to put in, and you choose soft start, it will put in a soft start without a voltage ramp. The reason, and it's called a step start. The reason for that is there are manufacturers out there that produce elevator controllers that are soft starters but do not have the voltage ramp. And that's a terrible thing. They're terrible to try to start on a generator, but that we're trying to take care of you, so that will be the default in the program. Anything but that, you generally are going to have a starter with a voltage ramp. So you want to pay careful attention when you're selecting your soft starter to determine whether it's a step start or a ramp start. And on elevators, I always select step start. On most other loads that have separate reduced voltage starters, I'm going to go with a ramp. VFDs are much better. We do have to worry about the harmonics, and we talked about that, but we also have to worry about regeneration. If you have a high-rise building and you've got a drive that is regenerative and pushing power back in, we can't push much power back into a generator. They can provide power, but they don't like to be pushed. And if you try to push power back into a generator, it's typically going to overspeed and then trip on overspeed. So on cable elevators, we typically say either make sure you have enough other loads on in the building that it can absorb that power, or the cable elevator manufacturer can put a DC bus resistor in there to prevent that regeneration. And that's a very common way to do things. UPS sizing, I'm going to go through this lightning fast. This is our UPSs, or this is not our UPSs. It's the University of Utah Data Center here in Salt Lake. We have 5 megawatts of generator there, and those are parallel generators. With UPSs, with passive UPSs, you generally need the generator to be 5 times the size of the UPS, but these are only for tiny little computers, like home computers, so it generally is still fine. Line interactive is not much better. It requires 5 times. So anything significant, we would ask you to go with a double conversion. And here the generator generally needs to be 2 to 2.5 times the size of the UPS, but that 2 to 2.5 times includes powering the UPS and also providing air conditioning and lighting and so on for that room. So that pretty much does it there. I am going to stop sharing this and see if I can share another screen. This is the Generac website. It's really difficult. It's called www.generac.com. And they are always changing the website, so I'd like to tell you how to get to the sizing program, but it always changes. Sometimes the sizing program is right on this page, but if you can't find it, then find your industrial products. Generac has residential products, commercial products, and industrial products, and you want to get over to the industrial. So let's go over here and see if we can find it. Here's business and standby, and there's industrial. Let's try industrial. And then let's go down, and you'll notice, I hope, there's transfer switches, mobile products. Well, it's not there. So solutions, let's go to solutions. Boy, I apologize for this. Let's go back. Sorry about that. Let's go to solutions here rather than products. And over here, it'll be solutions for business and industry. That sounds better. And if we go down here, it says Power Design Pro. That's the program that you want. Now, if you look over here, there's another sizing calculator, but that's for residentials. And you'll notice that it's under the residential column. If you want to go in and say, hey, I've got an air conditioner and 2 freezers and so on, and have Generac tell you what size residential generator you're going to need, that's the place to go. But we're going to stick with the industrial one. It's called Power Design Pro. It is free. And down here, you're going to say, try it today. Now, try it today is going to go right into the program because it recognizes my computer and it knows that it's me. If you've never been in this program before, then you're going to need to put in a username and a password and your email address and so on. We don't send you junk mail. But that's it, and then it'll get you into the program. Now, there are help screens, but I've never read the instructions here. I think it works just fine. It works kind of like a spreadsheet. So I'm going to create a new project, and I'm going to call it the Elevator Project. I could put my name and email if I want, but I'll save that. And then you'll notice down here is my Elevator Project. It's added those to my projects. If I click on that, I go to my first screen, I hope. Oh, I'm sorry, I've got solutions. And I can have several solutions. I can do 3, 4, 5 different solutions with different loads and different generators for the same system. So let's go down here and just fill in some things. I will just call this one my base solution. Right there. That's what I generally do. And then other solutions, I'll say, well, this one is my 10% voltage solution or what have you. So we just fill in our typical stuff. There's a stationary generator, 100 degrees elevation. I have 4,500 feet because that's a typical elevation in Salt Lake City. But elevation's very important, and the program will automatically adjust for that. We'll say this is 3-phase, 60 hertz, and let me change this just for fun to 208 volts. So I change that to 208 volts. You go up here, and this is your maximum allowable transients, your voltage dip, your frequency dip. You can put this in, and it will establish limits when it sizes your generator for the voltage dips and the frequency dips and so on, and also harmonics. Let's go down here and put in a natural gas generator. And then there's some other things in here, USA and Canada, the type of application, so on and so forth. So I'm just going to save those. Those are my general features. And then I'm going to add an elevator. So I will add a hydraulic elevator. So we've got hydraulic elevator number 1. And notice here it says group 1. You can either do steps or you can do groups. If you do a step, it's going to start every load in the step at the same time. If you do groups, it will start the loads one at a time in the group, with your largest load starting last. Let me just go ahead and put in a 30 horsepower. Got a 30 horsepower elevator. And notice down here, it says your starter, it's 350% current limit and is a voltage stepped. Well, I'm going to go ahead and change that to a voltage ramp. We've talked about this before. Most of the starters that we sell are voltage ramp, although I told you that elevators typically don't have a voltage ramp. It's got a centrifugal pump to start that compressor, so I'm going to use low torque at start, although I could use the standard torque at start, and that would be fine. But it would result in a slightly larger generator. Let me now save this, and you'll notice that we end up with a 50 kilowatt generator. It's site rated, in other words, for elevation at 48 kilowatts. And we have an upsized alternator. It's very important that you take a look at that. This has given us an upsized alternator. Our running kilowatts is 59%. Our peak kilowatts is 49%. Our maximum voltage dip was 11.5. We're okay there because we can tolerate 15. And our total harmonic voltage distortion is 10.8. I'm going to be okay with that because it's just for a fraction of a second, or maybe a second while you're starting that. And then there's a lot of other information in here. But now I'm going to go back. I'm going to use the little pencil, you'll notice over here, and that allows me to go back and change that load. And I'm going to change my voltage ramped to a voltage stepped. I would always use a voltage stepped, and since it's stepped, it's going to have full torque when it gets started. I would always use a voltage step on an elevator. Now remember, we had a 50 kilowatt generator before with a 70 kilowatt alternator. Simply by changing that one thing. Oh, notice, did I do this right? Current voltage stepped. Okay, interesting. Usually that will upsize the engine. In this case, the engine didn't need to be upsized, but notice this. My alternator went from 70 kilowatts to 130 kilowatts, so it almost doubled the size of the alternator. I can go through here and just add more and more loads, and it will go ahead and just do my automatic analysis. Now, when I'm over here, after I've done the automatic analysis, I generally like to go to manual, and I'm going to do the manual select. And you'll notice in manual, I have the ability for me to just put in any generator I want. So in this case, just for fun, let's put in a 40 kilowatt generator, because I think that's plenty big. And notice, whoa, now I have a 50% voltage dip. And notice the red comes out. Well, that didn't work. So let me go back to my 50 kilowatt generator. But notice when it does that, it puts in a standard alternator, and I have a 42% voltage dip. So obviously I'm not doing well here. But if I go with my 130 kilowatt alternator, now I'm back to good shape. So a lot of times I'm going to want to play with that myself, and I can put in any generator I want and see what it does. Now, when you're done, you can click this right here, and we will do a summary report, and it gives you a nice, pretty printout of the summary report. If you go over here, it allows you to give documentation. You can get specification, a sample specification. It's still, you're going to need to go through that and read it and modify it. It gives you install drawings, and it has a gas supply design lines. If you go over here, it actually gives you a calculator by which to size the natural gas piping. And that's very, very easy to do. If you're going to extend the exhaust, you have that. And finally, just there's a lot of features of this that I really like, but let me just point out one more, and that is this one right here. It says share project. Now, when I share a project, I could share that, and it will automatically take this whole project and put it in your Power Design Pro. And if I click share project, it's going to come up and just ask me for your email. So this happens a lot of times with our customers. Our customers will go through the size of generator. then they'll say, I sure like somebody else just to look at this and give me their opinion. And I'm kind of the same way. It's really nice to have a second person give you an opinion, and they may come up with something that you didn't notice. So we have customers that will go ahead and size this generator, and then they'll just share it with me or share it with their account representatives. And this whole thing appears in our Power Design Pro. We cannot share it with anyone else. Once it comes with us, the only person we can share it with is we can share it back with you. We can't send it to anyone else. So it's a little careful. We're trying to protect your privacy of your project and so on. But if I want, I can change that design and say I'm going to go with a different generator, or I'm going to change the loads or whatever. And then I can say, hey, send back my revised solution to you, and you will get back in your Power Design Pro my suggestion for a revised solution. So that's pretty much it. We went a little longer than we used to, but I think we're fine. So hopefully you learned a few interesting things there, and I'm going to turn the time back to Tyler Simmons.
Great. We have a couple questions that have come in. Feel free to continue to send in questions. The first one is kind of a three-part question. They asked for some typical values that you're going to see. So the first one is, what is a standard frequency dip percentage that you would see?
Okay, very good question. I tend not to look at the frequency dip too much because I don't care that much about it. But your standard frequency dip is typically 5 to 10% where you want to prevent. You don't want to go above 5 to 10%. And you're typically going to see frequency dips. Depends. If you're starting one motor on one generator, you're going to have a frequency dip in that range. If you've got a building with lots of loads, your frequency dip may only be 1 or 2%. But again, I don't stress too much out over the frequency dip.
The next value they ask about is, what is the typical harmonic distortion percentage?
So your typical harmonic distortion percentage, you want to stay under 8%. That is IEEE 519. They recommend that you have 8% or less distortion. Now, if you're just starting something like a soft start, like I say, I'm happy to go to 10 or even 11%, only for the portion of that start. And then, of course, once a soft start is started, then the harmonics go away, and then you'll probably go down to 2 or 3% harmonics. So when it's starting, I'm willing to go 10, 11%. When it's running, I like to stay under 8, or I should say 8% or less.
The last value is they ask what a typical XD.
XD, I think when they're talking about transient reactance. Now, the X is, of course, the symbol for reactance. The D means direct axis, which is generally what we use. And you have your synchronous reactance, your transient reactance, and your subtransient reactance. So your synchronous reactance is X sub D, your transient reactance is X prime sub D, and your subtransient reactance is X double prime sub D. When we're analyzing a motor start or we're analyzing harmonics, we want to use X double prime sub D. And you're generally going to see, generally when we say what's your generator alternator reactance, we're talking about that subtransient reactance, X double prime sub D. So that's typically 12 to 15%.
Okay, next question. If you've already installed a 200 kW alternator, can you later change that to, say, a 230 kW alternator?
Yeah, so the answer is, if you're saying, is it humanly possible? Well, yeah, it's humanly possible. Is it easy, or is it something you're going to want to do? No. Now realize if you've got a 200 kilowatt alternator and you go to a 230, that's a 15% increase. And that, if we're talking about cost, so your cost is going to be 15% higher, but you're only increasing the cost of the alternator, not the entire generator. So you're only going to pay something like a 5% premium. So if you are saying, boy, I'd like that 230, but I'm going to try the 200, and then if it doesn't work, I'll go with the 230. That's probably not what you want to do, because it's only going to cost you a 5% premium in that case to upgrade. If you have to change it out later, it's a mess. And most people would choose not to do it because of the expense, having to buy an entirely new alternator. The couplings, the mounts, everything are going to have to change. And there are times when most of the time this is not true, but in some cases when the alternator gets so big, we actually have to change the enclosure a little bit to accommodate that larger alternator. So my answer is it possible? Yes. Are you going to be willing to pay for it? Probably not, because it's going to be really expensive.
Okay, we had someone write in a question actually before the webinar, so we don't have a ton of clarification, but they asked specifically for considerations and precautions for dealing with the third harmonic on a generator that would be operating 24/7.
Yeah, so third harmonic is only the case with single phase loads. Now that doesn't mean a single phase system. That means single phase loads. So if you're going to have not a lot of single phase loads in a typical installation. Where do you find single phase loads? Well, you find them in computers and fax machines and things like that. But typically, if you've got a 480 volt system, you're going to have a delta Y transformer, and those loads are, and then you'll go from 480 to 208, and you're going to put your computers and so on the 208, and that delta Y transformer is going to get rid of most of your third harmonics. So we tend not to worry about it. However, could happen. You could have a 208 volt system, and that system supplies almost exclusively lighting and computers and so on. And then you certainly are going to have a third harmonic problem. My advice is, doesn't matter whether it's third harmonic or fifth harmonic or whatever. On three-phase loads, you're generally going to have fifth and seventh harmonics. On single-phase loads, you're going to have third harmonics. I would still use the Power Design Pro program. Make sure that the harmonics of your loads are entered correctly in that step where you're putting on those loads, and let the computer just go ahead and do that for you. And again, we want to stay under 8% voltage distortion.
Great. How big of a factor does elevation play in generator sizing?
Now, there's a great question. I appreciate whoever asked that. It depends upon the generator. So, number one, you may have the same engine on a 40, 50, 60, and 70 kilowatt generator. And so on the 70 kilowatt generator, you're going to have a lot of elevation derating, and on the 40 kilowatt generator, no elevation derating at your elevation. So that matters. Also, turbocharging matters, because as you know, when you turbocharge, you basically are increasing the pressure of the ambient air. And so when you put a turbocharger in general, your altitude derating is going to be a little less. So having said that, I will tell you that for diesel generators, typically you can go up to about 1,000 meters or 3,300 feet without derating. And above that, you have to derate the diesel. Some diesel generators could go as high as 7,500 feet before you have to derate. It's completely up to the engine manufacturer and how heavily that engine's loaded and so forth. Now on natural gas engines and propane engines, or we'll say gaseous engines, a good share of those start derating at 600 feet. Now you're seldom, I don't even remember a diesel engine that started derating at 600 feet, but with gaseous generators, it's not uncommon to see them start derating at 600 feet. And so you get up to 5,000, 6,000 feet, you could have a 20% derate on those things. So especially with natural gas, we're more concerned about elevation. Having said that, we're always concerned about elevation. Anytime you do a project that's over 600 feet, you should be concerned about elevation. And fortunately, Power Design Pro does that for you. You just put in the elevation that you are installing that generator, and it will automatically derate that generator, and it will tell you the rating of the generator and the site rating of the generator at that elevation. But elevation is extremely important, and especially for people in the Intermountain area, in Salt Lake, in Idaho, Wyoming can get really high. Please don't forget to put in your elevation and make sure you size that generator at elevation.
How do you rate rotary UPS size to be connected to the generator?
So a rotary UPS is has a big old flywheel on there, and instead of batteries, then that is going to have your, instead of getting your energy out of a battery, you're going to get that energy out of a rotating flywheel. And I hate to punt on this, but I have never actually sized a generator with a rotating UPS. It's not going to be too difficult, but it might be good to check with the UPS manufacturer and see what your maximum load is going to be and how quick that is going to hit the generator, and then let the computer sizing analysis do that for you. But that's going to take a little more work, and I apologize, just haven't run into that before, although rotary UPSs are not that uncommon. So I'd say talk to your generator manufacturer, talk to the UPS manufacturer, and I think it's not going to be too difficult to get the values and parameters to put into your sizing program and make sure that you're good with that. Again, remember that the generators are going to come right back to 480 volts, but you have that sudden drop, and until it recovers when you suddenly hit that generator with a load. And many UPSs are able to bring their load on gradually to allow the generator to adjust to it. And so that rotary UPS, you'd have to check with the manufacturer to see if they're able to bring that load on in a gradual way to allow the generator to adjust to that rather than hitting the generator with that load all of a sudden.
All right, there's another question that came in. Looks like basically they're asking where are generators made, and is there going to be major differences between American generators versus European or Asian generators? Are they pretty interchangeable?
They are not at all interchangeable, and that's a great question. The standards are very, very different in the United States from other generators. Now, we do the Generac generator line. I can tell you that Generac makes generators for the United States in the United States. They're all made in Wisconsin, and they're all to U.S. standards. One of the big issues there is the EPA. These generators need to be UPA compliant. Now, Generator also owns Automotores, which is the largest generator manufacturer in Mexico. You cannot use an Automotores generator in the United States because it does not meet American standards. And the same would be true with Europe. Europe tends to have somewhat standards that will work from one country to the next, like France and Germany and so on. But even there, it depends on what country you're in. And so, you better make sure that if you're in the U.S., you're using a U.S.-made generator or a U.S. Compliant generator. That's why in the sizing analysis, you'll notice that one place had USA because they size for generators in the USA. Do not use a European generator in America or vice versa. Also, in some cases, you may find that a generator appropriate for Colorado may not be used in California because California has higher standards, and so you need to make sure that that generator is rated for use in California. And generally, we're talking about emissions here, not anything else. There is also, of course, UL. UL in the United States is required. UL in Mexico or a lot of other places is not required. So hopefully that answers that question.
Are generators available for outdoor usage? Do they come with AC in the enclosure, or how does that work?
I'm not sure I understand that completely, but are generators available for outdoor usage? Yes, the lion's share of generators are outdoor. They come in their own outdoor enclosure. And generally what you're going to want to have is something simply to keep the battery charged. Whenever that generator is there, it's going to be sucking battery power from the battery in order to keep the controller on and keep all your stuff working. So if you don't have something to keep that battery charged, the battery's going to go dead in less than a day, and then your generator is not going to work. So we generally like to have On smaller generators, just a 120 volt supply, and larger generators at maybe 208 or 240, or in very, very large generators, even 480. And that does, it keeps your battery charged. Now, the other thing it does is we like to have block heaters on standby generators. More important with diesel than with natural gas, but still on at least larger generators, we like them on both. And block heaters try to keep the engine block warm. If you're going to have that diesel engine start quickly and reliably, it's got to be warm. They'll keep it to a minimum of 100 degrees Fahrenheit. And so that takes a little bit more power. But again, it's generally a 120 or 240 volt circuit. And so you need to have some power from the utility for those items in the generator. Now, once the generator starts, then it provides its own power. And so you don't really need power from the utility. But that's kind of how it works. And you can get outdoor enclosures in the standard enclosure, or sound attenuated level 2, which is even a little bit quieter.
Do most generator units come with HMIs and LAN interfaces for external monitoring and remote control?
Great question. So the HMI, all generators come with an HMI. Now, you might imagine that if you buy a Generac residential generator, that HMI is going to be pretty simple, because residential generators are going to be small, and it's just going to come with a LCD screen in there. If you buy a big generator, you may have that generator come with a full color touch screen on it. But all generators will come with some type of an HMI. And the more money you spend on the generator, generally, the better controller you get and the better the HMI. Now, in terms of communications, not all generators have communications at all. So typically, if you buy a generator that's residential or light commercial, you cannot talk to that generator, period. That's changing. And in Generac's new line, they're actually coming out with a Wi-Fi server in the residential line and Bluetooth. In all of our generators, the larger ones, we can communicate with them Bluetooth. You can actually communicate with them cell phone. They have a web server inside. Generator communications have typically been Modbus. So most of your industrial generators, you can communicate Modbus. And then if you wanted some other method of communications like Ethernet or LawnWorks or something, then you would have to buy a gateway in order to convert the Modbus to that. But gateways aren't too expensive. In fact, we can convert our Modbus to Ethernet generally for $150, with a standard tiny little converter. Now, the new controllers, as you might suspect, like everything else in society, are getting more and more sophisticated. And so as you get into the newer controllers, you're going to find more communications options.
As an add-on to that question, they asked, what about with multiple generators that are going to be used simultaneously? What controls will typically be used there?
So it depends. If you're talking about paralleled generators, then what we have is a communication link from what we call our system controller. I think about it as like a big remote annunciator. You'll generally put it inside, and so your communications will go from that system controller to all of the generators. And then if you want to talk to the generation system, all you need to do is talk to the system controller. So it's one Modbus communications or Ethernet communications, whatever you'd like. You talk to the system controller, and it communicates with everything else. Now, if you have 4 generators and they are not paralleled, they may be on different buildings or whatever, then you're going to have a separate communications to each of those. But then, clearly most communication systems, you can talk to multiple loads. So whether you're talking Modbus or Ethernet or what have you, you're still just going to have one input into your PLC or into your computer, and you can talk to those different loads.
Is there special hardware available for paralleling they've added on?
Yeah, so if you're going to buy a paralleling generator, and we will get into this in our paralleling discussion, but of course that's not this week, you have to have a paralleling generator. And generally that means that the generator must have a paralleling controller, a controller that has paralleling capability. You've got to have sensors for paralleling. They're going to have to sense the output voltage and so on so they can sync to it. And you're going to have a contact to parallel across, which could be a motorized circuit breaker, or it could be a contactor. And so if you're going to do integrated paralleling, then you need to buy a generator that is compatible with that basically is parallelable. Now, if you're going to parallel externally, that's a different thing, but you still need to be very careful that your generator is capable of doing that paralleling. So don't buy a generator and say, oh, I'll just buy it now, and if I parallel it in the future, I'll go out and upgrade it to a parallelable generator. That's going to be very expensive and difficult. Buy that parallelable generator right from the start. It is not that expensive to, it's not that much more expensive to buy a parallelable generator that's all set up for paralleling than it is a standalone generator. You're not going to pay a big adder for that. And so if you think you're ever going to parallel, make sure that you buy a parallelable generator. And of course, if you're buying a system of more than one generator, obviously all those generators are going to come configured as parallelable generators.
All right, that looks like all the questions we have. So we'd like to thank everyone for joining us, and we look forward to seeing you next time.